Okay, welcome everyone. So today is my pleasure to welcome Etienne Memim, who will be talking about ensemble forecasting and reproducing kernel Hilbert spaces or dynamical system in Wonderland. Yeah, thank you, Etienne.
Yeah, thank you, Boumediene. So thank you for the invitation and for giving me the opportunity to present this work. So this is a joint work with Benjamin, Dufay, Béranger, Hugues, who are two PhD students in my group, and Gilles Tissot is also is a researcher in my group, whose name is the Odyssey, and which is a group that focuses mainly on ocean dynamics, but we have some studies on learning of ocean dynamic systems. So the reason for this study. So in this study, we will try to see how we can mix ensemble methods and kernel learning types of methodology. And so I will explain why this family of reproducing kernel Hilbert spaces is called Wonderland. So, okay, so first of all, so a quick introduction. So there is a huge interest in for several years on ensemble methods. So either for forecasting issues or for data assimilation issues as well. So you have variational ensemble methods or filtering methods set as extended Kalman filtering, sorry, define an ensemble of realization. And the advantages of the main advantage of these ensemble methods is that they allows you to avoid the definition of the construction of an adjoint model of the dynamical system, which can be a very tough work that takes a lot of time in any case. So, but nevertheless, they rely on a questionable assumption of superposition principle, which is normally associated to linear system. So there is also a big interest in defining surrogate dynamical system, and so in that kind of work, you construct usually bases from data time series, and so there is this proper orthogonal decomposition techniques, for example, or dynamical modes decomposition techniques that are used to get these basis function. And one object of interest also is the Koopman operator, that I will recall just after, and we are interested in a representation of its spectral decomposition, and because it gives intrinsic basis function associated to the dynamics, meaning they are not in series associated with the initial condition of the system. So the Koopman operator, so given a dynamical system phi t, so you see my mouse? Yes?
Yes, we see it, yes.
Yeah, okay. And so the Koopman operator is U at time t is defined as a composition of an observable F, and as a composition of the observable F and the dynamical system started at the initial condition X. So the the value of ut applied to f at x is given by this composition. So it's a linear operator. It applies on functions, so it's in theory infinite dimensional, and so it may have a continuous spectrum, which is a problem. So it's not only I mean it's rarely purely spectrum. It depends on the dynamical system you are dealing with. So a lot of finite dimensional approximation have been proposed, but for example the dynamic mode decomposition, but it raises immediately a question about the eigenvalues that you're estimating. Are they representing or not the true eigenvalues of the Koopman operator? It's not immediate. So, but to work with, to propose, I mean, estimation methods for the eigenpair of the Koopman operator, you need, this requires usually some compactification methods, some regularization, such as those brought by reproducing kernel Hilbert space, or you need to work on ergodic system, and to sometimes even to make sure you have a point spectrum, and sometimes even to ensure that you have simple eigenvalues. So usually it requires a lot of assumptions. So and at the end, most of them allows you to get only projection of one observable of a given observable on the eigenfunction. So these modes are called Koopman modes, but they are not the eigenfunction of the Koopman operator. Okay, so we would like to take the problem with a different angle and to work instead of working. So all those techniques I mentioned before, they are mainly based on long time series of observables. So we would like to work with a different angle and to work on an ensemble of realizations instead of working with long data time series. And the objective is to learn locally the dynamics in order to synthesize new realization from the learned one. Okay, so from a set of realization, we would like to synthesize new realization without simulating them. So to do that, we will work within a family of time-varying reproducing kernel Hilbert space. So we call them affectionously Wonderland, because there is in this family of reproducing kernel Hilbert space, there is some striking properties. So you have the Koopman operator and its adjoint, which is the Perron-Frobenius operator, that are unitary, like L2, but like in L2, but they have bounded infinitesimal generator, which is not the case in L2. So meaning that they are uniformly continuous, and they are diagonalizable, and they can be expanded in terms of an exponential form. So it's quite strong. Beside that, we have also a rigorous ensemble expression the tangent linear operator that you can relate to this infinitesimal generator of the Koopman Perron-Frobenius operator. And for some choices, for simple choices of the kernel, you obtain the approximation that are used indeed in the ensemble Kalman filtering methods. And you obtain also quite easily some the Lyapunov finite time exponent that are directly related to the eigenvalues of the Koopman operator. So I remind first what are reproducing kernel Hilbert space. So these RKHS, they are Hilbert space. Here we will work with Hilbert space of a complex valued function on a compact ensemble omega, and given a kernel function defined on omega cross omega. This space is called reproducing kernel Hilbert space if you have the two following properties, which are the fact that the evaluation function, also called the feature map, belong to the RKHS H, and you have this particular reproducing property, which says that the inner product of a function of this Hilbert space with the evaluation function gives you the evaluation of the function at point X. Okay, so these properties provide you immediately an expression of the kernel, which is Hermitian and positive definite. So by the inner product of the two feature maps, you have the property that this evaluation operator is continuous, which is very particular to these spaces. And we have the results from node results from Aaron Sagin, which say that the Hilbert space are uniquely defined by the kernel and vice versa. You have the span of the feature maps over the set omega that is dense in this Hilbert space. And another characterization of this space can be done through integral kernel operator. So we define the integral operator LK, which is an operator from L2 to L2, which is defined as the convolution of the kernel with an observable, with a function of this Hilbert space. And so this is a well-defined operator. It can be shown to be compact and self-adjoint. So you have a Mercer theorem for it, which say that the feature maps Kx, which span the RKHS, they can be described from an eigenpair from the eigenpairs of the kernel K. Okay, so this is classical results, and these RKHS, they are spaces of smooth function with fast decreasing coefficients. So from this, you may define a square root of this operator. So elf power 1/2, which goes from L2 to this Hilbert space H. And so you have one operator elf1/2 that increases the function regularity from going to L2 to H, and then you have the inverse. This is a bijective operator, and so you have the inverse that lowers the regularity of the function by bringing them back to L2. So now we will use that for dynamical system. So in this work, we will take an invertible dynamical system, so described by this flow phi of t, so which says that the state of the system at time t is given by phi t of x0, the initial condition, and we assume that the system is defined it gives a compact, we have a compact invariant manifold for this system, so which is called omega. So this is x are functions, and so there are functions defined on spatial supports omega x, okay, and they are vectorial function of RD, and we assume that it is differentiable, so continuously differentiable, and it can be written in the form of this differential system, okay, and the differential operator M, okay, will be assumed to be C1 as well, and in order to have a well-defined linear tangent expression, because we will exhibit an ensemble expression of this linear tangent operator. It is assumed that the system has an invariant measure, and we will assume to have n trajectories of the system, starting from some initial condition, from n initial condition, and then we have n trajectories of the system. So, and for all the time t positive, we will we will have a set of states reached at time t. Okay, so this is called omega t. So omega t is the integration of all the point of the initial condition, and omega 0 is assumed to uniquely characterize the trajectory. So we have a unique initial condition that characterize a full trajectory, and we assume that this omega 0 is rich enough, so the set of initial condition is rich enough in order to cover the whole invariant manifold of the dynamical system. So if you have the union over t of omega t, you have the whole manifold of the dynamical system. At each time t, so at each time t, we can define a kernel kt defined on omega t cross omega t, and by that there exists RKHS that depends on this kt, a unique one. Okay, and we call this family of RKHS Wonderland. It's nicknamed Wonderland. So the kernels, they are defined in the following way. So the kernel at kt of xt yt. So the state reach after t integration of an initial condition x0 and y0 is defined by a kernel k0 that is given, and we take so the value of K0 at the initial condition of xt. So meaning that we invert the flow to get the initial condition from xt yt. Okay, and it could be also defined from an operator, so u cursive at time t, which goes from h0 to ht, such that the feature map k0 of x0, on which you apply this operator, gives you the feature map of the kernel kt that applies on omega t cross omega t. Okay, so in a way, this operator u cursive is transporting the kernel feature map on the RKHS manifold by composition of the with the system dynamics. So you can guess from this immediately that there is an isometry from H0 to HT. So meaning that the kernel are invariant along the flow. So you have the kernel at time kt evaluated at xt yt is equal to the kernel at time 0 at the initial condition evaluated at both initial conditions x0 y0. So you have u cursive and p cursive, the adjoint of u cursive, that are representation, the kernel representation of the Koopman and Perron-Frobenius. So in this family of RKHS, so in Wonderland, they are both unitary operator, and so to study them a bit more and to give the main results, so we define something that is related to the infinitesimal generator of both of these operator, which is the operator AUT, which is an operator that goes from HT to L2, okay, and which correspond to the functional derivative along the flow of the kernel, in fact. And so we will see that it is related to the infinitesimal generator of the Koopman operator defined on a bigger RKHS. But this is the object of interest, AUT. So we can show it is bounded and skew symmetric on L2, okay, for any function of HC. And this corresponds to, it gives us an evolution equation for the feature maps. And so we have then this theorem. So if we assume that the kernel we are dealing with is C11, so meaning that you have to take a differentiable kernel for the initial condition. C11 means that it is continuously differentiable in both arguments. And so with the kind of dynamical system we are dealing with, so meaning an invertible measure preserving dynamical system, so on a compact manifold, there exists an orthonormal basis, an Hilbertian basis, psi, that depends on T. So this is a basis of HT, which diagonalizes this operator AUT that goes from HT to L2. Okay, and so you have this eigen function decomposition. And then you see that the eigenvalue here does not depend on time. So there is this isospectral property associated to this representation. And we have a relation. We have an exponential relation between the basis function at time t and the basis function at time psi0. So the evaluation at point xt of the basis function psi t is given time up to coefficient depending on the eigenvalue is given by the basis function at the initial time evaluated at the initial condition. And as I said, the eigenvalues do not depend on time, which relates in a way this kind of representation to Laxper theory. So that's the relation between Laxper theory and Koopman operator is not new, but here it gives really direct relation. So so it means that in a sense we are representing only the integrable part of the dynamical system we are dealing with. Okay, so just a few words about the proof. So it's long, but it's not difficult. So you cannot work. At least we didn't find a way to do it, but maybe it's possible, but you can't work directly with this RKHS family. You have to, because you don't have a good topology. So you have to work with an embedding bigger RKHS, which includes all these RKHS. And so to do that, you define a kernel K that is defined from the kernels KT by adding with the product of another time kernel that depends only on time. Okay, and so you have a space-time kernel. Which relates directly this space HT to this encompassing RKHS H, and the time kernel is assumed to be, of course, symmetric, but it's a time it's translation invariant kernel. Okay, and you have also the value of this kernel that must be 1 at the origin. So you have relation between H and HT that are given through restriction and extension operators. They are isometries, okay, and they form an adjoint pair of operator. So so you can define also the Koopman operator on H and its infinitesimal generator. That is an operator that goes from H to L2, okay? And so so to have the demonstration of the theorem, you need to work on the diagonalization of this operator AU by working by studying a bijective approximation A tilde of this operator that you get from Lyon's Lax-Milgram theorem that is directly related to AU and whose inverse is compact and self-adjoint. So it looks like very much to the proof you have for the spectral representation of the Laplacian, in fact. Okay, so it's indeed very similar. So and then once you have the spectral representation of this operator AU, then you can directly get the spectral representation. It's really direct of AUT through this restriction operator. So yeah, and you have at the end that the eigenfunctions of AUT, they correspond to restriction of the functions defined on A. Okay, so so beside this spectral representation, we have two very interesting results, which say that from this operator AUT and the operator that allows you to go from HT to L2, then you have this representation of the tangent linear operator. And the you can show also that the eigenvalues of this operator AUT gives you the Lyapunov exponent associated to the dynamical system. And so this will be very useful in the estimation methods we are going to propose, the simple ones. So as an example, we will work with a barotropic quasi-geostrophic model, which is a very simplified oceanic model, in which you have two coupled equations. So you have something like a transport equation of what is called the potential vorticity, Q, okay? And this is transported by the orthogonal, the perpendicular gradient of a stream function, and you have an elliptic relation between this stream function and the vorticity associated to the flow, the vorticity associated to the flow being a part of Q, okay? And so this, you know it because it's given by the latitude, okay? So it's, you know everything by this. So this allows you, in few words, to step forward the vorticity of a dynamical system, and then to get from the vorticity the velocity and so on, and then you have a closed system. Okay, and the system is forced by a steady wind in the form of a sinus. Okay, so this is called the double gyre problem, but okay. So, and we will focus on two kinds of kernels, so the empirical one and a Gaussian kernel. So the evaluation of this kernel along the trajectories being invariant in our setting, so we can reconstruct the trajectories from the initial condition and the given kernel. So for a new initial condition, the reconstructed trajectories is expressed as the classical RKHS regression, so as a linear combination, in fact, of this of the ensemble, where beta, okay, is estimated from the kernel and given by this regression formula, a very classical one in the RKHS setting. So, and beta is constant over time. That's the striking property of this setting. So, so you have a discrete definition of AUT, okay, that is given by the ensemble member and the evolution of the kernel, so which is given by this direct expression of the operator AUT, okay, as a differentiation along the flow of the kernel, okay. But you have this isometric property which allows you to go back to the initial condition. So it's very easy to evaluate a long time the kernel. You have the eigenpair at any time that gives you an exact evaluation of the Koopman eigenfunction on this RKHS family for all the ensemble members. And we have the associated Koopman eigenvalues. And the fact that the eigenvalues are related to the Lyapunov time allows us to filter, in fact, the Koopman eigenfunction in function of the Lyapunov time. So meaning that when we can switch off gradually the fast modes when they have passed the predictability time given by the finite time Lyapunov exponent. Okay, so gradually we switch off the fastest mode of the representation. So this is how the Koopman representation can be used for this to represent, in fact, new members of the system by assuming that it's not an assumption, but I mean the fastest most when you passed over the associated Lyapunov time, then they are not expressive anymore. So this is an example of the vorticity of the solution, so the potential vorticity that we have for this setting. You have the best representation, the L2 representation that you can get from the ensemble, and then you have here the representation that you would get from a Gaussian kernel. Okay, so in this numerical setting, we will assume that we have 100 members, 100 realization from which we learn the system. Okay, and we have another 100 members for testing the reconstruction. Of course, the testing ensemble has not been used for learning the system. So here it is the reconstruction of the new of the test ensemble. And it's the error is average over the whole test ensemble. So in black here you have the representation by the mean, which is the worst you can do. Okay, so you represent just the solution by the mean, and then so we have several solutions there. So you have in red. In dot red, you have the reconstruction. So where we use this the isometry, so meaning that you evaluate the kernel at the initial condition, and we use this empirical kernel. So at a given time, which correspond to so to a physical time in between 15 and 20 days of evolution, and then you cross the ensemble mean, meaning that the reconstruction is becoming worse, or let's say worse, and then a bit less than the ensemble mean. Okay. Of course, obviously, before it provides a good job, meaning that we have less error, and the error is increasing with time, which is normal. In green and yellow, so green first, we have the reconstruction provided by the Gaussian kernel. So meaning that in this reconstruction, we are looking for a linear combination that is constant in time, and the evaluation is performed at the initial condition only because of this theory. And okay, so you have this green line that is well above this, well below, sorry, the red curve. So it's improving a lot the solution. In yellow, you have the representation of the same but expanded on the Koopman eigenfunction, and which gives you the same results, meaning that the representation in terms of the Koopman eigenfunction is correct, at least numerically. And then okay, and then in blue we have the representation in which we have filtered the Koopman basis by switching off the fastest modes when their Lyapunov time exceeded the prediction time. Okay, so at a given time, when you detect that the modes is associated to a too small Lyapunov time, then you switch it off from your representation, and then it improves further the solution. So associated to the mean error, you have the variance, also the error bar of the solution, and we see that the Gaussian kernel, which is not a surprise, is performing much better than the empirical kernel. So as a second numerical test, so we tried this framework on a simple data assimilation formulation, which is known as ensemble optimal interpolation, in which you try to minimize the discrepancy between observation and the state variable. H is an operator that relates the state variable to the observation. Usually the observation are incomplete, so you don't observe the full system, and then you have a classical regularization term that is expressed here in the RKHS. Okay, so this is quite standard. This is so-called optimal interpolation cost function, and we have a regularization parameter that has been fixed through L-curve estimation, and that's been fixed to 500. So we didn't try to optimize it furtr. So here you have an example. So you have the reference solution that is evolving. So at 3 different time, and we consider two cases. So one, first of all, so we considered observations that are organized along satellite source. Okay, so you observe only one line, so actually two lines. Okay, that is two tracks of satellites, and in one case you observe these two tracks. Sorry, only one day. Okay, so over I don't know about 100 days, you observe only once these two tracks. So that's the worst case. And in the other case, we assume that we are able to observe these two tracks every day. Okay. And of course, the system, the time stepping of the system is much smaller than a day. And so you have the reconstruction in the third column when you observe only so this very sparse observation in space and time, because you have only one observation at day 6, okay, and no observation at all otherwise. And this reconstruction, which is obviously better when you observe these two lines every day. Okay, so we can see more quantitatively the errors average on the test ensemble, meaning that for each member of the test ensemble we have a different observation. And we average after that all the errors obtained. So you see in black the mean, the reconstruction by the mean ensemble. In blue the reconstruction when you have only one single observation, and you can guess okay the time of this observation. And in yellow, we have the reconstruction when we have an observation every day, okay? And in red, it's the optimal reconstruction that we would get with a constant, a constant coefficient for the linear combination. Okay, so because that's what we are estimating at the end. That's the most striking maybe results of this framework, is that at the end we have to estimate only something that is a linear combination of ensemble members, but the linear combination is constant in time. So it's very amazingly simple. The kind of system at the end that you get. Okay, so I finished my presentation. So this setting provides us a theoretical setting in which we are able to estimate the Koopman eigenpairs from a set of realizations. These ensemble of realization are embedded in a family of RKHS that evolves in time. That's a trick with kernels that are related to the initial condition of the system and that are kept invariant along the flow. So this setting provides access to an ensemble expression of the finite time Lyapunov exponent and of the tangent linear dynamics, which is very useful in ensemble data assimilation filtering methods, for example, and which I think generalizes the kind of approximations that are used in that kind of techniques. So that should broaden the kind of solution that can be imagined for such filtering. And at the end, we get very simple, embarrassingly simple data assimilation techniques that seems to work. I mean, they are giving quite encouraging results for very sparse observation. So at the moment, we are working on generalization of the or more complex filtering techniques associated to this framework. So we are implementing ensemble Koopman filtering on a piece of trajectories with this framework. Thank you very much.
Yeah, thank you very much. Thank you. Any questions or comments?
Yeah, I have a question. Could you please go back to the slide where you show that the Koopman operator is unitary in Wonderland? Because I didn't understand that.
Where I shown that so the Koopman operator it's a known result. So I don't know to which slides you're referring to.
It was like about 11 or something.
Okay. This one?
I think it's, yes, this one.
Okay. So the Koopman operator is unitary in L2, so that's a known result. Okay. And the adjoint is Perron-Frobenius. Here we have the Koopman operator that is defined on this evolving RKHS HT, and we have shown it's still unitary, which is not really surprising. I mean, because your HT is dense in L2, so.
But the Koopman operator, is it always unitary?
Sorry.
The Koopman operator, is that always unitary, or like?
No, not always. No.
Right?
It's unitary on L2 only.
On L2, so
I think so. Yes.
I see. And then I had another quick question about the relation between the spectrum of the operators in Wonderland and the spectrum of the original operators. Does that depend on the choice of basis functions too?
Okay, you are referring to the relation between the if I understood well your question, you're referring to the relation between this U-cursive operator, right? And this the operator UT, the Koopman operator on L2.
That's right. Yes, that's right.
Okay, so how can I say that? U-cursive, in fact, is a kernel representation of the Koopman operator, big UT, if you want, on L2. It's an operator that applies mainly on the feature maps.
I see. What does that say about the spectrum then? The spectrum.
Oh, okay. So then you can show that they share the same eigenvalues and eigenfunctions. Yes, I mean, there is a relation between the space HT and L2, okay? And there is a relation between HT and H, a bigger space, which encompasses the whole family of RKHS.
Okay, I see. Okay, thank you.
Okay, and so you can go from one to the other, and when you have an eigenfunction for example on the RKHS, you have this square root operator LK power 1/2 or -1/2 that allows you to get the eigenfunction of the Koopman operator on L2.
I see. Okay, thank you. Thanks.
Other questions? I had a question about one of the figures where you talk about Lyapunov. What is like Lyapunov kernel or?
Sorry, I did not understand.
Yeah, one of the figures. I mean, can you go to the figures? I mean, I saw that something called Lyapunov kernel or.
Oh no, I don't know. I don't know anything about that. So
yeah, I saw it in the figures. I mean, like one of the. Can you go to the next? Yeah, here. So you see. Yeah, okay. Lyapunov filtered kernel blue. What is this?
Yes, this is the okay. This is the results when you filter, when you remove in fact the Koopman eigenfunction in your representation, when the Lyapunov time, so the predictability time of a given basis function, eigen function of the Koopman operator has been passed. So meaning that it's too fast. In fact, you're removing, in fact, gradually the fastest modes of this representation. So slowly by slowly, you're keeping, in fact, only the slow modes.
Yeah. Okay. Yeah, that's good. And actually, I had a question like similar to Dominico's question about like the impact of the choice of the kernel. So if, for example, here I have you choose like a Gaussian kernel.
Yes.
And what happens if you change the variance, or if you have different kernels? What would happen?
Yeah, it depends on the kernel. The results definitely depends on the kernel. So so we didn't work on this, and it would be very interesting to estimate this bandwidth. We didn't. In fact, we fixed it just by trying few values for the standard deviation of the kernel, but that's all. So
nice. Yeah, in one of my papers, we are like learning kernels for dynamical systems. So I wonder how you would.
I know,
because your work is quite good, so it would be nice to see how you do it the other way around, where you learn the best kernel in a way.
Yeah, I know that would be an excellent idea. We didn't apply your results yet, but that's an excellent idea. Yeah, I saw that. I saw that.
Yeah. Anyway, we should maybe talk like later.
Yeah.
It'd be nice to see. I mean, this is like a nice framework. And then when in your other previous theorem where you are linking, I mean, can you come back to the few slides, like the previous, your main result about the link with Koopman? Yeah, this one. Yeah. So here, I mean, yeah. So I mean, this is like really nice. But then I wonder, what's like for a C11 kernel? I mean, is it like what was the impact of changing the kernel here as well?
Of the regularity of the kernel.
Yeah, either regularity or the kernel itself. You know, for example, Gaussian, you change the variance, or you have Gaussian and then a polynomial kernel.
Yeah. Okay. So in the paper, I don't have the results. Yeah, we tried only two kernels, so Gaussian kernel and empirical one, and definitely that there is some differences between the two. So you have the most difficult eigenvalues are those that are close to zero. These are the most difficult to estimate. And the Gaussian kernel allows you to estimate smaller eigenvalues than the empirical one. The empirical one gives you bad results very quickly, in fact.
Okay, nice. I mean, I think a nice advantage of Gaussian kernel is that you have you know the feature map analytically, so you can do things analytically.
Yes, exactly.
Yeah. Okay.
It's
Okay, that's very good. Yeah, thank you. Yeah.
it's a nice kernel for that.
Yeah, that's right.
Hmm.
Other questions or comments? All right. Okay. Thank you very much for the nice talk, and then looking forward to seeing you again. Yeah. Thank you. Bye bye. Bye everyone.
Thank you very much. Bye.